Hi everyone. In this chapter we will be studying relations and functions. In this lesson we will be looking at function notation. But before we do, let's review the idea of a function.
Okay, so in this lesson we're going to take a look at function notation, which is a really important bit of notation. Okay, you've been looking at different definitions thus far in your math. You consistently learn new things about how to deal with variables and whatnot, and some of the rules. Now you're going to look at just a change in notation here that is going to really improve our ability to communicate in terms of mathematics here. So first of all, let's review what we mean by a function. Okay, it's a relation that's either one-to-one or many-to-one, but not one-to-many. Okay, so a couple of things here. Just remember, it assigns a single value of the to the dependent variable. It should say it assigns a single value of the dependent variable for every valid input, every value of the independent variable. So every time you plug in a value for x, you're only going to get one value of y. Okay, you can check this on the Cartesian plane by simply using that vertical line test. If it is at all possible for you to draw a vertical line through this relation and hit the relation more than once, not a function. If it's a function, you can only hit it once. Okay, and in a given equation here, we're always going to want to solve for y before we write it in function notation. So we're going to be looking at function notation here in a bit here, but we need to be able to solve for y first. You'll see why that is in a second here. Now, before we get into the nitty-gritty of function notation, let's take just a look at an example, again, talking about the representation of a function. So what we want to do here for this example here, we're going to graph the equation y equals 3x plus 1 over the domain -1, 0, 1, 2 for the domain, and then for the domain of real numbers here. So we're going to go to our table of values first here. Now we're going to throw in our domain, and the given domain right now is -1, 0, 1, and 2. So these are the specific values we're choosing. Now remember, y depends on x. How does y depend on x? Well, to get y, I'm going to multiply the x value by 3, and then I'm going to add 1. So I'm going to multiply this value of the independent variable by 3. So 3 times -1 is -3. And then I'm going to add 1. -3 plus 1 is -2. Down here, 0 times 3 is 0, plus 1 is 1. Okay, 3 times the independent variable, 1 here, so 3 times 1 plus 1 is 4. Okay, here 3 times the independent variable is going to be 2, so 3 times 2 is 6, plus 1 is 7. And what you need to know here is that this really is the y coordinate. Okay, this is how y depends on x. Here, if I just say y, okay, put this down, I'll get -2, 1, 4, 7. But this doesn't really give me an indication of how they're related. This is exactly how they're related. I take the independent variable, multiply by 3, and add 1. This idea of how they are related is really important for us to move forward in mathematics. Just listing a bunch of numbers here, numbers here, and then saying, okay, here's our point. That's good insofar as it goes, but it doesn't get us very far. Now we're going to plot these points. Okay, -1, -2, so -1, -2, there we go. 0, 1, 1, 4, 2, 7. Okay, 2, 7 takes us right off the graph there. Okay, and now we were supposed to do this for 3, but if we plug 3 in there, 3 times 3 is 9, plus 1 is 10. If you're to go up to 3, we're going to be way up here. Now, that is just for the given domain here. Now, if we go for the domain of real numbers, because we can plug any real number in here, what we've just done here is we've given you a bit of a... Sorry, I put that in the wrong spot. We're going to take these points that we just plotted over here, we're going to plot them again. Okay, 1, what was it? 1, 4, and then up here. These are just the points here to give us an idea of the trend. We can now just connect these dots here because it's a safe assumption here that the pattern established by these individual little finite points there can be connected indefinitely or in between along the interval there, in between those points, and extended beyond. And so this is what the graph of that function looks like. Okay? Now, we're going to take a few minutes. We're going to talk about function notation and how it relates to what we just looked at here.
And now we'll take some time to introduce the idea of function notation.
All right. Now, as it says here, in the above example, we often use x as the independent variable and y as the dependent variable. Now, that's not always the case. And even if it is the case, oftentimes we want to have multiple graphs on the same grid here. And simply using x and y every time doesn't allow us to differentiate between them. Okay? If I just use y equals, I never really get a sense of, if there's multiple graphs there, which one you're referring to. And then again, there are situations here where I really don't want to use x and y. Maybe I'm talking about, distance and time. Okay, where I'm moving along a road, for example, and my distance depends on the time that I've traveled. So these are other things where I need a little bit more flexibility with the variables here. Now I want you to understand what we've got established here when we say that y is equal to 3x plus 1. Okay, in this particular case here, now remember, y is our dependent variable, x is our independent variable. Now the question that I have for you right now is, how does y depend on x in this scenario? And the best way to get a sense of that is to look at what the relation is in words. Now, we haven't often, in the last little bit here, used words, okay, as a way of representing a function. But right now, it becomes really important that you catch this. In this particular case here, the dependent variable, okay, the dependent variable is 3 times a number. Now that particular number is the independent variable. So 3 times the independent variable increased by 1. That is the relationship that we have here. Now notice I'm using the words independent variable, dependent variable. Because no matter what the relationship is, you're going to have an independent variable and a dependent variable. Now, those variables could be something other than x and y. They could be x and y. But whatever it is, the dependent variable is, there's my equal sign, is 3 multiplied by the independent variable increased by 1. Now, because we could have multiple functions on here, what I want to do here is I want to create a notation that I can use to pick this one out in particular. So I'm going to introduce this idea of function notation. And so what we're going to do here is we're going to replace, okay, we're going to replace y with this little bit of notation right here, the f, and then in parentheses right behind it, we're going to have the x. Okay, this is read, okay, you read this f of x, or f at x. Okay, this little f of x, f at x here. And this is going to replace y. So instead of our dependent variable being y, our dependent variable is now going to be this f of x. This is not f times x. I cannot hit that point hard enough. This is not f times x. I know in different contexts that would be, but as soon as you see this pattern equals something over here, this is function notation, f of x. Now you might look at this and say, oh my gosh, why are they replacing a single value, a single variable with this whole bit of symbols here? Well, it's because of what this represents and what we can do with it. Now in this particular context, oh sorry, this should have been 1. Sorry, that should have been a 1 right there. In this particular context here, what the f means, okay, the f is going to be the rule of dependence. How the dependent variable depends on the independent variable. So f is going to represent that rule. It's going to represent the dependent variable is 3 times, okay, now I'm running off the screen here, 3 times the independent variable, okay, increased by 1. Okay, that's what the f means in this notation. Now, the parentheses x, when you put something in parentheses here. Now, it doesn't really matter what's in parentheses, okay? Basically, this is saying the independent variable is x. Now, if you had an a in there, then that would mean the independent variable is a, okay? Whatever shows up in parentheses, that is the independent variable. So here, the dependent variable is 3 times the independent variable, okay, x plus 1, or 3x plus 1. That's what this notation means. Now, the beauty of this is, let's say I had a different function altogether, okay? Let's say down here, just because I needed some space here, let's say I now had g of x is equal to x squared minus 1. In this notation here, g would mean this. The dependent variable is the independent variable, probably going off screen here, yeah, the independent variable squared less 1. And then remember that whatever's inside here, this is the independent variable is x. So g of x here means the independent variable squared minus 1, and the independent variable is x. So x squared minus 1. So now if I'm dealing with two different functions here, okay, I can, when I refer to them, when I refer to f, you would know in context that that means 3x plus 1. If I refer to g, I'm referring to x squared minus 1. Okay, it's really powerful for us to have a way of talking about functions and being able to differentiate them, okay? Your mathematics is going to take a substantial step forward here, a leap forward, really. Prior to this point here, you've used variables x and y, but x and y typically referred to numbers, specific values. Now, f and g here don't refer to specific numbers, they refer to specific rules, and we're going to start to do math on the rules, the actual relationship between numbers. It's kind of neat here. So let's just zoom out here a little bit and let's talk about this. Using function notation here. So what does it say? He says, well, the rule is the same up here. Whether you're talking about y equals 3x plus 1 or f of x equals 3x plus 1, the rule is the same. But now we're going to give it a name f. Okay, f is the name of the rule. F represents the rule. Okay, and again, the best way to describe that is it represents the rule in words. That might give you the clearest understanding of that. And so now, altogether, the rule plus an idea as to what the independent variable is, that's going to replace the dependent variable y. This is exactly representing the dependence that y has. Okay, up here, how does y depend on x? Well, you multiply 3 by x and add 1. So in this case, multiply by 3, add 1 is what f means. The x in the parentheses is what you're multiplying by 3 by, and then adding 1 to. Okay, so in this case, like it says here, the rule tells us to multiply the independent variable by 3, add 1 to it. So we use f of x as a way of identifying which variable is the dependent variable, and really which the whole thing becomes the dependent variable. I hope that makes sense. I know at first it looks like we're making a simple idea more complicated, but really what we're doing is we're making our notation far more user-friendly in the long run, okay? Because now as we advance through kind of new levels of mathematics, this function notation is going to make certain ideas a lot clearer. All right, well now what we're looking at here is really not much of an example, more it is just a little bit more explanation. Let's say right now that we know that y is equal to negative 2x plus 7. Okay, so that's how the y variable depends on the x variable. Multiply by negative 2, add 7. To put that into function notation, all we really got to do is just replace the y with f of x. Okay, is equal to negative 2x plus 7. Now in this particular case, the f, okay, the f is going to now be the rule. The dependent variable is negative 2 times the independent variable plus 7. Okay, that's the rule. That is now, in this context, what f represents. And again, this is just to reiterate that what we do is we read that as f at x. But something that I didn't say here is we only use this notation for functions, which is really why we typically use f here. You can use whatever letter you want to represent the relation here, or the functional relation, but normally we'd use f. F for function. Now, look over here. Let's take a look at a slightly different example here, just to kind of build on this here. What if f of x was now 3x plus 2 in this case? What happens if you change the independent variable? Okay, so let's say now, what this means right now is f means multiplied, and maybe I should identify this. In this particular case here, f means the dependent variable is 3 times the independent variable plus 2. Okay, plus 2. Now, what if, we'll zoom in here, what if they change the independent variable to t? Well, the rule stays the same, only the variables change. So the rule is multiply the independent variable by 3, add 2. But in this case here, we're identifying that the independent variable is now t. So this becomes 3 times t plus 2. Now, if that makes sense, okay, that whatever this is, whatever's inside there takes the place of the phrase independent variable here, then we can start to use this in a way that I hope will start to really clarify why this is such a nice tool here. What if we then say f of 1? What if we put an actual number in there? Instead of f of t, it now becomes f of 1. Well, now the rule is still the same. Multiply the independent variable by 3, add 2. But now the independent variable is taken on the value of 1. So multiply 3 by 1, add 2. 3 by 1 is 3, plus 2 is 5. So the answer is 5. But remember what this is. F of x, f of whatever's inside there, that is the dependent variable. So right here, we see a very clear relationship between the value of the independent variable and the dependent variable. So right here, I can see that the point 1 comma 5 would be on the graph of whatever this function is. See, you don't have the ability to see that direct connection if all you're doing is using x's and y's. Function notation really allows for some clarity when we're working with functions. Now, there's other things that we can do with function notation here, but we're going to start and kind of review what we've done here with the next few examples. All right, so in this example, we're just going to write the following in function notation. Now, I want you to see how easy this is, how easy this can be here, okay? So to write this in function notation, we are simply going to replace y with some function here. Now, it can be, for example, it could be f of x equals 10 minus 3x, okay? But it could very easily be something like this. We could leave it as y and write it as y of x equals 3x. Just in this case, we're going to use the variable y to represent the rule and the relation. Just like here, we could, for example, make this f of, now in this particular case here, it makes more sense to stick with the variable here. It's clear that the independent variable is b, so we'd say f of b is going to equal 12b squared minus 5. But again, because we're free to label the function whatever we want, we could also use the variable that they've got right there and just make this a of b is equal to 12b squared minus 5. It's just getting used to this notation here and remembering that whatever's inside is the independent variable. Okay, that the whole thing together is the dependent variable. So in this particular case here, we're not saying that a is the dependent variable. We're saying a of b is the dependent variable. A is just going to be the name that we give to the relation. Here, we might want to write this as s of t is equal to 2t plus 9. Okay, so now in this case, we're not going to use s as the dependent variable anymore. We'll use s of t. S will now become the name. It's just a convenient letter to use when we're converting from this one to this one. Same thing here. Perhaps maybe we would use v of x is equal to 17x minus 9. Now, the purpose of these next two here is to push us to do something first before we start writing this in the function notation. I got to get y by itself first. So I'm going to add 4x to both sides. So this will become y is equal to 4x plus 25. And so now, maybe I use function notation. And maybe when it's y, maybe I go back to f of x it doesn't really matter. I could make that y of x if I want, but there you go. Same thing here. What I got to do first is get the y variable by itself. The dependent variable here by itself. So 2y is going to equal negative x minus 6 when I subtract those two terms. And now I got to bring the y over. So I'm going to divide everything by 2. So negative x over 2 minus 3. And so now this is what the dependent variable is. And so now I can replace it with my new representative of the dependent variable, f of x. And that's going to equal negative x over 2 minus 3. Okay, so that's really all there is to function notation. Okay, here's a good example, really good example. I hope that by the time we're done this, function notation is starting to really set in here. So we're told that given that f of x is equal to 4 minus x and g of x is equal to 2x squared minus 3, evaluate the following. Okay, so what does f mean? Well, f means that the dependent variable is going to be 4 less the independent variable, whatever that is. So in this case right here, notice what this is. What is f of 3 then? Well, f of 3 becomes the independent variable. So the rule is 4 minus the independent variable. So this becomes 4 minus 3, and the answer is 1. F of 3 is 1. And so that implies that the point 3 comma 1 is on that graph. Basically what I'm doing here is whatever is in here, there should be an x here, right? This in the proper form of the notation, this should be an x. Well, that's the same x. This is exactly the same x. So whatever goes here has got to go here. So if I plug a 3 in there, that's got to become a 3 as well. Look over here, g of 1. Okay, g, the rule for g is we're going to multiply 2 by the square of the independent variable and then subtract 3. In this case, we're told that the independent variable is 1. So this is going to be 2 times the square of the independent variable, which we already know is 1, and then we're going to subtract 3. And now we just let order of operations take over. 1 squared is 1, times 2 is 2, minus 3 is negative 1. So g at 1 is negative 1. So there's the relationship here. The point that would be on the graph would be the point x comma the y coordinate, because remember this function notation is going to refer to the dependent variable on the graph, typically y. So the point is 1 comma negative 1. Whatever's inside, whatever I'm replacing the x with here, I replace the x with here. Okay? I'm not multiplying everything in front by 1. I'm replacing the x here. I'm being told that the value of x is now 1. Now over here, what does this mean? What does it mean to have the 2 in the front? Well, order of operations still holds. So I'm going to deal with what's in brackets here first. Okay? So this is going to be, I'm going to deal with this f of x first. Now, f of x is going to be something, or f of negative 1 is going to be some value. There's going to be a 2 multiplied out front here. I'm going to do that later. But what this means is I'm going to go to my f function here, which is 4 minus x, 4 minus the independent variable. The independent variable here is negative 1. So inside the brackets here, 4 minus negative 1. Okay, so 4 minus negative 1 is going to be 5. And then I multiply by 2 to get 10. So that multiplication by 2, that comes after you figure out what the function is equal to. So 2 times f of negative 1 is going to be 10. Over here, in this particular case here, notice all we're really doing with this function here is replacing the x with t's in both cases here. So f, and I'm going to put brackets around the thing that represents f and brackets around the expression that represents g here. F of t will be 4 minus the independent variable, and in this case I know that it's going to be t. G is going to be 2 times the independent variable squared, in this case the independent variable is t, minus 3. And now I would add those together, and I'll put it in standard form here, so the 2t squared will come first, minus t. The only like terms are the constants here, so 4 plus negative 3 will be positive 1. So that's what we get when we add f of t to g of t. 2t squared minus t plus 1. That is what this is equivalent to. Now we're going to do a very, very similar sort of thing. It's just this time, in both cases, we're going to let the independent variable become 0. Again, I'm going to put parentheses around the representatives of the functions at that value there. So f, remember, is 4 minus the independent variable. Here the independent variable is 0. So f is 4 minus 0. There's f. G was 2 times the independent variable squared minus 3. Well, in this case, the independent variable is 0. So this will be, and remember, in parentheses here, 2 times the independent variable squared minus 3. Now I'm just going to evaluate this. This is going to be 4 minus, well, 0 squared is 0, times 2 is 0, but I'm going to be left with this minus 3 in here, inside the parentheses here. And now I can focus on this little bit right here. 4 minus negative 3 will be plus 3, so 4 plus 3, 7. F at 0 minus G of at 0 would be equal to 7. And so, like now, I hope you're starting to get a sense of the power of this. Now we can do math with functions. Not just with variables representing numbers, but with variables representing functions, representing relationships between the variables. It's really neat here. F of a. What does this mean? Well, this means that in the function f, the independent variable is going to take on the value a. Well, that's just going to be 4 minus a. That's all I have to do. Whatever I see in here replaces the x, or the independent variable, in function f. Now compare that with this one right here, g of 2x. Now this is going to be, this is kind of confusing at this moment here, but I hope we can get past this. The independent variable here is 2x. And I know someone's going to say, no, 2 is not a variable. Yeah. But the way it's written right now, this is your independent variable. Now think about what g is. G is 2 times the independent variable squared minus 3. Whatever shows up between those parentheses is the independent variable. It doesn't bother me that there's more than one factor there. That's what this is. Now, after you do the work here, then the independent variable will become just x. But until we get into that function here, this is the independent variable, 2x. So this becomes 2 times 2x, there's the independent variable, squared, minus 3. There's the independent variable in the function. Now we're going to evaluate this. 2x squared will be 4x squared, like this, minus 3. And so that'll just be 8x squared minus 3. And once you've got it written like this, now in an expression like this, now that things are expanded out and reduced here, if we were to look at this here, we might actually call this by a new function name. This was g of 2x. But you might actually even give this another name here and just call this some function h of x. Because now I've got this new expression, and this would make it clear that the independent variable is equal to x, just x. Can I really do that? Yeah, of course I can do that. That's not a problem at all. It's not a problem at all. If we're looking at this in terms of just the function g, then the independent variable is this expression 2x. But I can always give that another name, okay, and identify the independent variable then as just the x here in this. So yeah, I can do that. Anyway, but you need to know what to do when there's an expression in here. That's going to become even more poignant when we look at something like this, g of x minus 2. Oh, okay, wow. Well, what does this mean? Well, this means that the independent variable is this binomial x minus 2. So now think about what g does. G multiplies 2 by the independent variable squared and then subtracts 3. So this is going to be 2 times the independent variable squared minus 3. X minus 2 in this case is the independent variable. So we're going to do something like what we did over here to help give some clarity to this. Now, order of operations says I square this first. Please, I beg of you, don't tell me that this is x squared plus or minus 4. This is going to be x minus 2 x minus 2 minus 3. So in brackets, you're going to do this multiplication first. This will be x squared minus 4x plus 4 minus 3. If you're wondering where that negative 4x came from, it's because you're not distributing properly. Okay? It's a really common mistake, but you got to get past this. If this is a mistake that you make frequently, if you're the person who kind of consistently makes that x squared and then just square the 2, you've got to figure out a way to get past that because that's wrong. And now you would distribute the 2 through, make this 2x squared minus 8x plus 8 minus 3. And now we've got like terms at the back here with the constants. So 2x squared minus 8x plus 5. Now this is g of x minus 2. All the way down, that was g of x minus 2. So this is what you get when x minus 2 is the independent variable in g. I don't like thinking about x minus 2, though, at the end here as being the independent variable, so I would label that as h of x equals g of x minus 2. And so now I've got an expression, okay, where I'm just going to let x be the independent variable, and that feels more comfortable. Okay? Don't worry so much about this use of h of x right here. I just need you to know what to do if you've got a binomial inside my function notation. Okay? One other question in this example, at least I think it's just one other question. Yeah. F of x is equal to 12. Well, what does that mean? Because notice this is an interesting one here because the value that we're given is equal to the function. It's not inside the function. The function is equal to it. Well, let's just think about this. Well, what is f of x? F of x was 4 minus x. So that was equal to 12. So this is really, when it's written like this is an equation to solve. The function notation is so powerful, it's so interesting. As soon as you set the function equal to something, that's an equation you got to solve. Up here, for example, f of 3, f of 3 is not an equation to solve. Okay? If you know what the independent variable is, this is just an expression to evaluate. I just want to know, what is f of 3? What does it equal? But if I tell you that f of x is 12, then the unknown is the x. I have to solve for it. And so what I might do here is subtract 4 from both sides to get negative x is equal to 8. And then divide both sides by that negative in front, and now get x is equal to negative 8. And so as soon as you've got something like that, where the value of the dependent variable is given, but not the independent variable, the expectation is that you're going to solve that resulting equation. Such powerful notation. All right, now here's another example. It's a slightly more complicated example, but we've already seen this concept. So if p of x is equal to 4x squared minus 6x plus 1. Now, and remember, the choice of variable name, it can be anything. So what does p mean in this case? Well, p means multiply 4 by the independent variable squared, then subtract 6 times the independent variable, and then add 1. That's what p means. And then what's inside here identifies what the independent variable is. Now, this is, by definition, what p is. Now we're asking you to evaluate what is p at x minus 3. This is becoming the independent variable. So think about what p says. So p of x minus 3 means 4 times the independent variable squared. That's what this is. Okay, the independent variable here is x, 4x squared. So what's the independent variable here? X minus 3. Then we're going to subtract 6 times the independent variable, and again the independent variable here is x minus 3, and we'll add 1. Okay, so now we just got to jump through the hoop of doing the arithmetic here, or sorry, the algebra here. Okay, this becomes 4 times x minus 3 times x minus 3. And I know I said it just a couple minutes ago here, but please don't be the person who just distributes the square to both of those terms. That's incorrect. This is 6 times x minus 3 plus 1. Now we're going to distribute, and this will become x squared minus 6x plus 9. This will become negative 6x plus 18 plus 1. And then we'll distribute the 4 through, so 4x squared minus 24x plus 36 minus 6x plus, okay, well that's going to be 19. And now putting together those terms here, 4x squared, we've got minus 24x minus 6, those will be minus 30x. And then I've got 36 plus 19, that's going to be, what is that, 55. So 4x squared minus 30x plus 55. That's what you get with px minus 3. Now, this is what it looks like, okay? This is what p looks like when x minus 3 is the independent variable. And by the way, there's nothing really wrong with that, with using an expression here, because remember, in this particular case here, do I know at this point what x is? Well, no, that's an unknown. So if x is an unknown, then I don't know what x minus 3 is either. So yeah, there's no problem with x minus 3 being considered the independent variable. I mean, it's a little bit more complicated because it's an expression, but it's as unknown as x. However, I might now write this as f of x, okay, maybe relabel this whole thing as f, so that my independent variable can just be the x here. And again, I'm totally free to do stuff like that. Just so long as you understand that this is what it looks like in P when the independent variable is x minus 3. All right, now, this example right here, this is a wonderful example because it's a beautiful crossover with function notation and the graph here. So we're giving you the graph of f of x. Okay, so some function here, some relationship between the dependent variable and the independent variable is drawn here. All of the ordered pairs that are possible on this graph are represented right here. So now what we want to do is we want to find f of, we want to evaluate, these expressions right here. Now, this is actually very, very easy to do, assuming you understand what it's asking. Now, f of 3. So I want to know what the function is when the independent variable is 3. But remember that this whole thing together, and it's so hard to remember this, I know, but you got to. You've got to spend some time and commit this to memory here. This is the dependent variable. And when we're talking about a graph, the dependent variable is y. Okay, remember that the dependent is y, the independent is x. So what I'm asking for here is what is y when x is equal to 3? And so we come across here to x equals 3, and I look for the graph. Well, here, when x is equal to 3, this is the point right here, and the corresponding y-coordinate here is -1. Okay? Then I come over here, same question, just with a different independent variable, value for the independent variable, -3. So I'm looking for the y-coordinate. The whole thing is the y-coordinate when the x-coordinate is -3. So I come over here. Where's -3? Well, -3 is right here. And now I'm looking up and down this line for the graph, and there it is right there. And it turns out the y-coordinate in this case is -3. So the dependent variable is also -3. Over here, get same thing. F of -6. This whole thing represents the dependent variable. -6 is the independent variable. So -6 is x. The whole thing here is y. So -6, I come across to -6. And based on what we're seeing here, the function looks like it should be going right through that point here. So the y-coordinate would be 0 here. So f of -6 is going to be 0. I hope that made sense here, because what we're doing is we're just asking you to find points on the graph here. And the points that we're looking for in the first case here was 3, -1. Okay? Remember, independent variable is x, dependent variable is y. For the second one here was -3, -3. Independent variable was x, dependent variable is y. Over here, the point that we're looking for is -6, 0. The independent variable is -6. The dependent variable is 0. Okay. And you can do this in the other direction here. State the values of x if f of x is equal to 3. Now, bear in mind that at this point here, this is a significantly different statement. This is now an equation that needs to be solved. I need to solve for x. I need to get what x is. Up here, it isn't. This is just something that gets evaluated. You are plugging the value in for x and just figuring out what you get when you do that. Here, I'm telling you that the result is 3. I want to know what the value of x was that created that. This is an equation, okay? These are equations to solve. Okay, so now let's go. Where is the dependent variable 3? Now the dependent variable is y. So we're going to go up to y here, and I'm going to slide back and forth until I hit the graph right here. And then notice that the x value here for that particular point is 7. So I've solved that little equation. X is equal to 7. Here, this one right here, f of x equals negative 2. Okay, so remember the dependent variable is negative 2. So okay, I'm going to come across here negative 2. Okay, whoa, I got a bunch going on here, because when I go across at negative 2, I'm getting values here, here, and here. I've got 3 different values of x that do that. So x is going to equal, let's just list them off here. What was the first one? Negative 4. Yeah. Come over here. Negative 2. And then over here was 2. So negative 4 is one of them. Negative 2. And then positive 2. And now finally, this one right here, again, this is the dependent variable. I know that the dependent variable is negative 4. So I come over here to negative 4, and I go back and forth along this line here, and notice that actually the graph never does reach down this low. Okay, there is no function along there. So that makes this actually a lot easier. There's no solution. And that is totally fine. Okay, it's totally fine to get a result where there is no solution. It's always possible that there's an equation that doesn't actually have an answer. Okay, let's take a look at this next example here. Carmen works for a research company in a shopping mall. Okay, the equation P is equal to 5n plus 30 represents her daily pay, P dollars, when she conducts n surveys. So describe the function here. Okay, write the equation using function notation. Okay, so the function relation that we've got here is the dependent variable. And in this case, the dependent variable is going to be her pay, is 5 times the independent variable, which in this case is n, okay, plus 30. So in function notation, we might write it as P of n is equal to 5n plus 30. And this is a direct expression that P depends on the value of n, right? This is the independent variable, and then this is how it depends on n. P depends on n, okay? This is how. And if you think about that up here, in this initial expression, without the P of n there, there's no indication of what P depends on. Okay, in fact, you might not even know that that's the dependent variable at this point here, but P of n, as soon as you write it like this, I know that this whole thing is the dependent variable and that n is what it depends on. Find the value of P of 8. What does this number mean? Okay, so P of 8, our rule has stayed the same, but the value of the independent variable has changed here. So this will be 5 times, remember, it's 5 times the independent variable. Now it's 5 times 8 plus 30. And so 5 times 8 is 40 plus 30. P of 8 is equal to 70. Now what does this mean? Well, this means she gets $70 for doing 8 surveys. I think it was, surveys. Now let's take a look at this one. Find the value of n when P of n is equal to 90. See, now there, again, this is an equation that needs to be solved. Up here, P of 8 was just an expression to be evaluated. This is an equation to be solved. So P of n is 5n plus 30. Okay, that is how P depends on n, and this expression is equal to 90. So the dependent variable, what this thing is equal to, okay, so if you just look at my function notation, P of n is equal to this. And now what I'm doing is I'm saying that this part right here is 90. We're going to solve for n. I'm going to subtract 30 from both sides, and that's going to get me 60. So n is going to equal 12. So what does this mean? It means to get $90, she must do 12 surveys. Now, would this be continuous or discrete data if you were to graph it? Well, now let's think about that. Okay, without a context, okay, if you were just to graph the relation P of n is equal to 5n plus 30, without a context, you might be justifiable in saying that this is continuous data, not knowing any better here. But you can't do a part of a survey, okay? You also can't do, can't get paid or you don't get paid, I should say, in values that are all along an interval. Okay, basically money is not continuous here. So this one here, if you were to graph it, you can't. Well, I suppose you could. Sorry, I suppose you could do a portion of a survey. It might work something like this: like she gets no pay here, comes across here, and then as soon as one survey happens, her pay jumps up to here. And now she's doing the other survey, but she's not going to get paid for it until it's done. As soon as it's done, boom, she gets paid that number. So a graph that looks like this, we would call discontinuous. That's probably the best way to think about that. Okay, you might think of it like this as a discrete thing. She does no survey, she gets no money. 1 survey, 2 survey, 3 survey. It doesn't really take into account the fact that she could be partway through a survey. Okay, she's not going to get paid for that. It's not her income isn't going to jump up at that point. But you could think of it like this as well and make it discrete. But I think this is probably the better way to think about it as discontinuous. Is this a function? Yes. Okay. And why is it a function? Well, just think of this right here. Is it possible to plug in a number in for n and get 2 different results? Particularly here when the only operations are going to multiply by 5 and add 30. Okay? Nah, it's a function because every value for n will produce a unique result. Okay? Not only will it produce just one result, not just a result, okay, but a unique result. Turns out this is going to be a 1-to-1 function. Okay. Yeah. If you plugged in, for example, n was 5 and then n is equal to 10, like you'll never get 2 values of n that actually produce the same value. It's not just that n will only produce one value, but every value that it produces is unique to that value of n. So it's 1-to-1. All right, now for this question here, we're gonna learn a little bit about the graphing calculator. So we read here that the height of a diver on a board, or diving off a board really, can be expressed by the function 32 minus 4.905 t squared, where h is the height, the diver's height above the water in meters, and t is the seconds after jumping off the board. Now we're going to use a graphing calculator to answer a couple questions here. So I'll show you how to do this. Okay. So first of all, grab your calculator and we're going to press y equals. That's going to open up this list of y values here. Y equals, y equals, y equals. This is because the calculator can graph a bunch of different lines at the same time. Now, our function here, okay, is what we're going to enter. Remember, this is the y-coordinate. H of t is the y-coordinate. Now, our calculator is assuming, though, that the dependent variable is y, the independent variable is x. So you just got to make that transition in your head here. And so the equation here is going to be 32 minus 4.905. Now, instead of putting t squared, I'm going to put x squared there. This is where I'm going to grab x. This button right here is the variable button. Now you can grab the other x by using the alpha key here, but this is the one that's usually the quickest way of doing that. Just press x right there. So it drops the x there, and then we'll square that. Now, I'm going to press graph. Okay, now, this is an interesting one. My graph shoots up, it goes off my screen, and then comes back down again. So what I'm going to do here is press the window button right here. Because what this does is this tells me where the sides of my graph are. the x min is negative 10. The x max is positive 10. The y min here is negative 10. The y max up here is only positive 10. I need that y max to be bigger. But I don't know how big it's supposed to be, so I'm just going to take a guess at it. Let's just say 50 and see what happens if I press graph. Ah, okay, well that was good. That was good enough. Yeah. Now, here's the line that the diver jumped here. So now the question is, determine the diver's height after 1.5 seconds. Well, there's a nice little way of doing that. Okay, 1.5 seconds is a value of the independent variable. So really what we're being asked to evaluate here is h of 1.5. Let me show you how. So we're going to press second, trace, and the one that we're going to use here is the one value. I'm going to choose value here. Because as soon as you do that, the calculator is going to wait for you to plug in the x value. So we're going to plug in 1.5, and it'll take you right to that point right there, and then the y coordinate here is 20.96. Okay, so 21.0, and we round it. Okay, 21.0. Now, I'm going to show you another way of doing this. Okay, quit. I'm going to show you another way of doing this that is going to look a little bit more like function notation. I got to make sure that I've got the function written down here, okay, in y1. Once I know that there's a function in y1, I'm going to quit. Go back to my home screen. Now, there's a very seldom used button here, but it really should be more on people's radar. Vars. Okay, I want you to press vars right here. The reason I want you to go to vars is because the calculator stores everything in a variable, and if you look right at the top there, it's got the y variables in it. So we're going to go over to the y variables. Which of those words do we recognize? Well, function. We've just been working with functions, so choose number 1. And now this is a list of all the different functions that the calculator had. The y1 equals y2, y3, blah, blah, blah. We just entered a function into y1, so choose y1, press enter here. Now, what you can do is put in brackets 1.5 just as if it was function notation. This is like f of x here. The calculator will know what you mean. It knows go to y1 and plug 1.5 in for x, and when you do that, you get the 20.96 that we saw before, or 21 when we rounded. Okay. The next question here is going to be estimate how long the diver was in the air. Okay, that means going back to the graph here. Now, what we're trying to do here is we're trying to figure out here, remember, now it doesn't make sense to look at the graph over here because this is negative time. Time is along the x-axis, this is negative time, doesn't make any sense. So the diver jumped here, hit the water here. So all of this, it represents him in the air. So we need to find where that graph hits that x-axis there. So to do that, we're going to press second, trace. And the thing that we're going to look at here is the zero function. We're interested in when the function goes to 0. Okay, it's this little equation here. What we're interested in is where that function h of t is equal to 0. And once we know what that t is, we will know when how long that diver was in the air here. So we're going to choose number 2. And now I got to find that point here. Now the calculator has a pretty specific way of doing this. So here's roughly where that point is. It's not exactly correct. I'm going to make that better here. First of all, I'm going to use the arrow key, move to the left, press enter. So what I'm doing is I'm putting a left bound on the calculator's work. Now I go to the right. I just move past the x-intercept that I'm looking for here, that value where it crosses the x-axis. As long as that point right there is in between these two arrows here, that's where the calculator is going to look. Now, the calculator is going to guess this right here. It's asking you if it's okay to start with this number here. Now, don't worry about the guess. The guess is just a way of speeding up the calculator's work. Just press enter to get past it. And we get here that when x is equal to 2.6, okay, 2.6, actually, sorry, not 6.6, just 2.6. That's when the diver has hit the ground. Ah, water, yeah, not the ground. That would be terrible. Okay, so now write an appropriate domain. Well, this is a continuous graph. The domain refers to the amount of time that the diver's in the air. So the domain here is going to be time will extend from 0, and we just saw, out to 2.6. Okay, and time and height are both continuous, so this is going to be a continuous graph. Okay, neither one of those variables there is discrete, so this is just going to be a continuous graph. And the range, well, how high did it start to begin with? What was the original height? What was this value right here? Well, we got to figure that out. And so to do that, I'm going to go second trace. I want to figure out what the value is, okay, at the very beginning. Because, I mean, how high was this person up when they jumped? So let's plug 0 in. And we see right there it was 32. 32 was the highest height that this person is at. So their range is going to be all values of the height from 0 when he hits the water up to 32, the initial height that he was at. Okay, there you go. Hope that gives you a little bit of an idea of how you might use the calculator to answer these kinds of questions.